I'm going to be talking about Kubernetes just for 10 minutes, so I'm not going to clearly talk about too much. But what I want to talk about is taking it to the limit. So, who here knows Kubernetes, just before I start talking about it? Okay, so a few people, cool. Who's actually using it? Okay, a fewer people, okay. You should already use it. First of all, before I start talking about that, people are probably familiar at the moment using VMs. So I think people are beginning to use containers, but I think that most of us are still in this world of using VMs. They're easy to use, easy to set up. And with the likes of Amazon, for instance, we can easily spin them up. We end up with sort of doing this sort of thing. I'm sure people are familiar. You set up a microservice, and you spin up a VM, and then you spin up another VM, and then you spin up another VM, and you get this sort of so-called VM sprawl problem where you just have like so many of them, and you're not really quite sure which what's actually spinning and what's actually doing anything you need. So this is what it might look like in prod. Of course, you might have something in staging, and what you end up with is just so many of these things. If you would actually look at the resource utilization on those VMs, you might actually find that they're not really doing very much. Right, so the database that you thought was going to be busy isn't very busy. The application server that you thought might need to be used isn't being used. So if you look at the utilization, you might actually really find that there's not a lot really being done, despite the fact you're paying Amazon handsomely for this, which they're really happy to receive. And of course in like staging, it's even worse, right? Because maybe you're just doing nothing with staging and you're just leaving it on like over the weekend, and no one's really using it. So you've basically got like oodles and oodles of like spare resources. You've got CPU cores, you've got memory that you can use to do something. However, you've got like no really good way of doing it because you've geared everything around spinning up a VM, installing all your dependencies, and you kind of know the story. So this kind of costs money. I guess as developers we care less about that. I guess managers care about money, but I mean we can all save the world though. So actually trying to save power is actually I think a pretty reasonable thing to do. So enter containers. I won't talk about the virtues of containers. I think everyone has kind of been hearing about them, using them. But what's pretty nice about containers is you're not going to be basically taking the entire operating system, Linux operating system. What you're doing is just bundling all your applications, or your application and its dependencies into a container, and then just using like a shared kernel. So you're effectively using the virtualization built into the kernel. That's pretty awesome. So you've got a number of schedulers that have been built on top of, or orchestrators, that have been built on top of the container runtimes, like Docker, for instance, or like Rocket. And what's good about this is they can start to play this kind of Tetris problem of, I have all of these compute machines, I have all of these machines, and I want to basically now take the workloads that I've got and basically put them efficiently into what I've got. Basically, it's like squeezing, like playing this game, right? And trying to get the best fit possible, which is pretty good. Before doing that, I just thought I'd introduce Kubernetes for anyone sort of goes, I'm not quite sure what it is. What's really quite good about Kubernetes is it's been built based on basically the way that Google's been managing its data centers for the last 15 years. And they're pretty damn good at it. They've been using containers way before even Docker was even thought about. Docker popularized it. Google have been doing this for some time. They've been using a system called Borg, which is effectively their workload scheduling system internally. So if you're a developer at Google, you're working on like Drive or Gmail or something, you don't really actually know where your actual software lands. All you know is how to describe to the system, Borg in this case, how to get that workload into a vast set of compute. And we're talking, I think, tens of thousands of nodes per cell, and you've got multiple cells across the globe. So you're talking about sort of millions of machines. Clearly, you're not going to want to install it on one particular machine. So what they did is they open sourced what they'd already done. It's called Kubernetes. It's been around for about 2 years. It's also like several different ways of pronouncing it. Kubernetes. But effectively it's a Go implementation of pretty much what they've done internally. It's not exactly the same. What they've done is kind of learnt the lessons of what they did well, what they did badly, and they've then kind of handed it back to the open source to say, we've been doing containers for some time, we think we're pretty good at them, we think you may benefit from this. So it's pretty awesome because it's actually one of the first times Google has really written a paper and then gone out and actually done an implementation of it, because ordinarily they've written the paper, MapReduce, Bigtable for instance, and someone else has kind of had to go back and sort of implement it. And part of the really good technologies that we've got have come from those papers. But this is actually where Google have done it themselves. And the one really interesting thing is, if you actually go and follow the project, it's on GitHub at the moment. It's like the most active project on GitHub, I think, at the moment. Maybe bar one, maybe it's about second. What you'll find is a lot of the people who are contributing to it, like wider industry, but the actual guys from Google are the guys who are actually working on their internal system, which is, I think, pretty awesome. You're getting the guys that have actually been working on it firsthand, and are now actually working on the open source. And you can sort of get this for free, which I think is pretty awesome. So the whole idea is, if you're wanting to have containers and you're wanting to run them on lots of compute nodes, lots of VMs, bare metal machines, you're going to need something that can effectively do the scheduling and orchestration. So it has to take your workload and put it onto all of that compute resource. But you also need a bit more than that. You need to be able to, for instance, monitor it, you need to scale it, you need to auto-heal it. The idea is that you can take a lot of the ops pain away by having a system that can help you do it. That's probably all I've got to talk about it, but if you have a read of it, it's an incredibly interesting system, as is the paper. Basically, it's split into a master and a set of nodes. So we've got a control plane, it's got a bunch of components which are doing things for us, basically. Lots of control loops which are making sure that our view of the system, how we want the system to look, is actually the way the system looks. So it's basically reconciliating that desired state with the actual state in the system. So we're having to do very less work. Basically, we sort of say, I want to run an application, I want to run 5 of them, go do it. And it goes and does it. It goes off to the various nodes, each running an agent called a kubelet, and the kubelet then interfaces with the Docker runtime and actually runs your container. So you're not having to type Docker run each time you run a container, because if you want to do that across like 1,000 machines, it becomes a problem. So this is doing it for you. So you've got master, control plane, all backed by things like etcd, and then you've got a set of nodes, kubelets. So the kubelet is what's of interest here. Now when you actually run a pod ordinarily, or a container, you have multiple containers inside a pod. You basically specify to it exactly what you want to run. So in this case, I'm just running, this is just an example container from Google themselves, just running, it basically serves the host name. And there's a bunch of other parameters here. This is all YAML. This is basically how you describe how you want your application to look and how it to run. The image, for instance, the port that you want to expose, a bunch of labels maybe, so you can find and identify it later. One of the interesting things I want to talk about here specifically is about how the kubelet's able to help, or at least Kubernetes is able to schedule effectively. So what it's going to do here is, in my case, what I've done is I've added basically a request for a resource. And this basically said, look, when I run this, I want to make sure I have at least a CPU, and I want to have 512 megabytes of memory. So this is what I need to function to run. Now, by doing that in the piece of the YAML, you basically inform the scheduler, and the scheduler now says, okay, right, so I've now got a piece of knowledge, I need to run this application, and I now need to figure out pretty much where to run it. So the scheduler can use that, and it uses the request to make sure that it can place that workload correctly, which is basically finding like the most available, the well-fitting, kind of well-fitted spot that this will go. Now, if we don't put any limits on it, and that particular container, or the process inside the container, were to kind of continue eating up all this resource, what you might end up with is a situation where you basically continue growing, eating resource, eating CPU, eating memory, for instance, and then you kind of hit this horrible OOM, which people will probably be familiar with. And if you've ever experienced it on your laptop, on a Linux laptop, it just kills your laptop. And it doesn't generally come back to a pretty stable state afterwards. So basically, OOM is something you really, really want to avoid. And if anyone's seen this in production, you'll know exactly what I mean. You really don't want that to happen. So in Kubernetes, you can go a little further. You can make a request for resource. That's my request, this is what I want it to run. But you can then basically add a limit. And then you can do this with a container if you're using Docker. You can add like a limit which says, I really don't want you to go over 512 megabytes of memory. That's basically your limit. You can't possibly go over it. And if you do, then I'm going to do some kind of piece of action to kill you, for instance, or to move you somewhere else. It's incredibly useful. And this resource control is done using C groups in Linux, if you've ever read about it. So it hands it all down. So what I'm doing is I'm making a request in YAML saying this is what my limit is. It gets passed to Docker, and then Docker then passes that down to the kernel. All done for you. It's just pretty magic. But in Kubernetes, it goes one step further. What you can actually do is, by basically requesting these requests and limits, what Kubernetes does is it determines implicitly your quality of service for your container. So it classes it, basically. It puts it into a bunch of classes. So one is like best effort, basically. So if basically I didn't specify any resource constraints or any limits whatsoever, it's regarded as just being best effort. If, however, I do make a request, an option has set a limit, then it's regarded as being burstable. So it will start with the minimum amount of resource I ask for, and it will be able to burst. So it'll be able to use, for instance, the available memory or available CPU calls. And if I set both the limit and optionally the request, then what I get is something that's guaranteed. Basically, this process is really important. try not to kill it. And what it does using that quality of service is it's able to rank all of the processes which are running on the system. And it's able then to influence which one gets killed if OOM does happen. So if resource start to get starved, it will basically look at all these pods or these containers, and then it will rank them and determine the ones that it will kill. So what that means is the best effort ones, the ones that really haven't got any constraints set, will be the first to be killed. But the ones that are guaranteed, i.e. things like are really important, even like system daemons for instance, are not the ones to kill. So you're basically influencing the way Linux does OOM, which is pretty neat. This is what the kubelet's doing together with Linux. So that's pretty neat. Some algorithm that's does some kind of magic to get you those kinds of numbers. But the one really interesting feature beyond that is eviction. So this is a recent feature that went into 1.3 and 1.4. If you're following the releases, that's kind of something quite recent. What it's actually able to do is it's able to preempt OOM even happening. Because you don't really want that to happen, to be honest. You really want to get to a situation where you can preempt it entirely. The kubelet is pretty clever. Using quality of service, it can basically watch for when it's under memory pressure or CPU pressure or disk pressure. No CPU pressure, just disk pressure and memory pressure right now. And it's able to basically preemptively evict stuff. So in the background, what this is doing for you is it's basically moving the containers which are just gobbling resource and moving them somewhere else, such that they don't affect your high priority processes. I think this is pretty neat. You're not having to do any of this. This is all being done for you under the bonnet. So what would happen basically is if you lost, let's say, one of these pods, it's moving, then it just gets moved somewhere else. This is going from node to node. It's basically being rescheduled. And what's happening under the bonnet, I haven't got too much time to go into the detail, but effectively, basically each node is reporting when it's under some kind of pressure. It sends out a signal. The signal then is received. And basically what then happens is this node gets marked as being under pressure, and hence the scheduler can use that when it's scheduling. So if you want to go and put another best effort pod on, it's not going to happen. It just gets avoided, and that then gets positioned, that then gets scheduled somewhere else until such time that this node comes back. What does this all mean? Well, you can do clever things like overcommit. You can basically give many, many more processes than the machine can actually really handle, and then use something like this to preemptively move stuff about. So basically what you're doing is you're using the spare compute that you've got to basically get the best bang for buck. And this is exactly what Google do. They don't want to build a new data center each time they've got another new product that comes along. What they really want to do is use all the existing resources they've got really, really efficiently. I think it costs them like $250 million to build a data center. So if you can save building another one, it really makes sense. And they've managed to raise the efficiency of their data center much, much above what we're used to. I think typically it's really low. I think the average enterprise is like 13% resource utilization, so you're paying for 100% of the resource and only really using a very small amount of it. So I think stuff like this is really smart because it can start to use your VMs and basically use everything, the resource that you've got. I think it's a really interesting tweet. I would have shown you a demo, but it's a lightning talk. Clearly, I can't do it anymore. But one of the guys actually behind this is one of the Google developers behind this. He said Kubernetes nodes are almost indestructible. So what he means is you can just throw workloads at these nodes, and you've got the kubelet, the agent, which is trying to chuck stuff off when it's under pressure and moving it about. So I think this is pretty neat. It also sounds like a bit of a challenge. So if you fancy writing something that can test that and putting that to the test, I think I'd recommend you do. This is me. I'm from JetStack. If containers float your boat, if Kubernetes floats your boat, if you write Go, come and speak to us. We're heavily recruiting at the moment. Cheers, thank you.